Good morning, friends and dear student. I am really impressed upon my course, Engineering Thermodynamics, and today this is the one of the last topic of this course. After this, I will have one more class about numericals on heat transfer. So this is not last, but one before the last. I am Dr. Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, for this course, Engineering Thermodynamics, I have covered the basics of thermodynamics that relates to the properties of the substances. The properties, those who are intrinsic or pressure, temperature, specific volume, specific enthalpy, specific entropy. Also, we have done about the dryness fraction, conversion of water to vapor, and what the process is taking place in that latent heat. Zeroth law of thermodynamics, first law of thermodynamics, work and heat, and conversion of work from heat. In zeroth law, we have also find out the temperature scale, how to measure the temperature by use of thermometer. In the second module, we have learned about second law of thermodynamics. The second law of thermodynamics gives that there is a efficiency which is not 100%, means every heat or every energy cannot be converted to a useful work. There will be some losses. Those losses are measured by the help of the efficiency of any system. In this respect, we have find out the absolute temperature, the inequality, Clausius inequality, the relation between heat and the work, and we have find out the internal energy in this concept. When moving to the module 3, we have done about the psychometric, wet bulb temperature, dry bulb temperature, humidity, percentage of air in humid and all. Then we have to go to the module 4, which is the power cycle. In power cycle, we have learned the 5 cycle. Out of 5 cycle, 4 power cycles are the power generating or work generating cycle. Those are the Otto cycle, diesel cycle, dual cycle, and the Brayton cycle. Out of these 4, 3 are the reciprocating type or intermittent cycle, and the fourth one, that is the Brayton cycle, is a rotary type continuous power generation system. Another one is the power absorbing, that is for heat pump or for the refrigeration and air conditioning system, that is the Bell-Coleman cycle, which we have done very well, and we have done so many numericals on that. As of now, I am in the module 5. This module 5 relates to the heat transfer and the compression. The heat transfer part I have completed before this class. We have done few numericals also. Few we will be doing after this also. 4 to 5 numericals on heat transfer we will be doing after this class also. So in heat transfer we have done about conduction, convection, radiation, their resistance method for the conduction, resistance method for the convection, for the composite wall, how much resistance is there, only for the conduction, how much resistance is there. This all the parts we have already covered. Today I am going to discuss about the topic which is very much important, that is the efficiency of the air compressor. So why we need the compressor? You might have seen that in my previous classes, especially in module 4, when we were discussing about power generation or the power cycle. In the power cycle, everywhere the first and the most important cycle is the compression. Compression we are doing as a reversible adiabatic or the isentropic process. In that, we assume this is the ideal condition and there is no generation of entropy. There is no change in the entropy. Entropy is remain constant in the compression process. So in the compression, we have to use some type of compressors. Those compressors we have already studied some types of the compressor, and now in this we have the reciprocating type and the dynamic type. In the reciprocating type, we have the piston engine and positive displacement. In the positive displacement, we have the reciprocating and the continuous type. In the reciprocating type, we have the single stroke, double stroke, and in the reciprocating, we have the screw type, axial flow, and so many things are there. When we talk about the dynamic compressor, we have the axial flow compressor and the centrifugal flow compressor. These dynamic type of compressor are the continuous operation compressor, mostly used in the gas turbine engine, for the power plant, for the aircraft, like a turboprop engine, turbofan engine, turboshaft engine, turbojet engine. Everywhere we use the dynamic type of compression. Mostly we use the axial flow compressor on that. So we have done this thing in my previous class. Today I am going to take in this efficiency of the air compressor. So in this we have the content like isentropic efficiency of compressors, numerical on the compressor efficiency, volumetric efficiency of reciprocating compression, derivation of volumetric efficiency. So these topics I am going to cover today in this lecture. So I will start with the first one, that is isentropic efficiency of a compressor. So in this we can see that the isentropic efficiency of the, so what is the meaning of isentropic? You see that whenever we have discussed a PV diagram or anything of the engines, so 1 to 2, this is the isentropic compression. Then 2 to 3 is the your isochoric heat addition. Then this is the isentropic expansion, and this is the isochoric heat rejection. So it is a isentropic expansion, and this is the isentropic compression. Okay, so what is the meaning of isotropic? So if I draw the TS diagram here itself, a small TS diagram, if I draw, T and S. S is a entropy. So in this 1 to 2 will be the vertical line. Then 2 to 3 is a constant volume line. Okay, I will make it like this. Then 3 to 4 is a isentropic expansion, and 4 to 1, 2, 3 and 4. So here 1 and 2 and 3 and 4 both are the isentropic compression and expansion. So in this you will see delta S is 0. Both the this, so this is called isentropic, means there is no change in entropy. So the isentropic efficiency of a compressor is defined as the ratio of the required input the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work output. So in this actual work output and the isentropic work output, it is the ratio of these two things. So we see here in this diagram. Here I have drawn the diagram of enthalpy. This is the enthalpy, and this is the entropy. And here you can see that one thing is 1 to 2s and 1 to 2a. This 1 to 2 is actual process. In the actual process, if I draw the vertical line here, there is some change in the entropy from here to here. But from 1 to 2s, it is a vertical line. S2s is equal to S21. But this S2a is not equal to S2s or S2s1. So there is a difference in that. So if you see this H2a is greater than the H2s. So the work done by this H2a minus H1 is greater than the H2s minus H1. So if it is not isentropic, the work we have to give more. More power has to be used to counter this change in entropy. So the isentropic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work output. So actual isentropic work output divided by actual work output, it will give the isentropic efficiency. So we can say that eta C, that is eta for the compression, is equal to isentropic compressor work divided by actual compressor work. So what is the isentropic compressor work? It is H2s minus H1. And what is the actual work? Compressor work? H2a minus H1, where H2a minus H1 is greater than H2s minus H1. So this is the Ws by Wa. This eta C will be H2s minus H1 divided by H2a minus H1. So this you can see here in this plot. For the actual process, we have this H2a, this H2a, and for the isentropic process, we have the H2s. So this H2a is greater than H2s. It means the enthalpy which is generated by the isentropic process is less than the entropy generated by the actual process. So H2a minus H2s, there will be some positive number. So the efficiency of this compressor will be H2s minus H1 divided by H2a minus H1. So this is the isentropic efficiency. But normally we use in compressor we use another term that is called the isothermal efficiency. So what is the meaning of isothermal efficiency? If you see here this plot here, we should maintain a constant temperature. So air is entering in the compressor, and here this you can see entering is more volume, and as it is leaving it is less volume, and it is rotated by some device, some motor or something. So it is rotating. So here air is entering from this side. Air is entering from this side. Slowly it is moving, and due to this rotation of this thing and due to the reduction in the volume of this thing, pressure will be increased. As pressure is increasing, the temperature of the gas will also increase. So we cannot tell that this compression is isothermal. To make the compression isothermal, we have to cool this area. We have to put the cooling water around this compressor so that the temperature will be maintained. In my previous classes for this heat transfer, it is done by the radiator or some cooling devices. Those cooling devices are used to maintain the constant temperature. Otherwise, temperature will not be maintained constant. So, a realistic model process for compressor that are intentionally cooled during the compression process is the reversible isothermal process. Then we can conveniently define an isothermal efficiency for such cases by comparing the actual process to a reversible isothermal one. So we have to compare with the reversible isothermal process with the actual process, and then if you divide the reversible isothermal process by the actual isothermal, then we can say that it is a thermal efficiency of the compressor. So this thermal efficiency of the isothermal efficiency of the compressor, eta C is equal to WT, work produced, work in the isothermal process, and actual work done in this process. So we have seen these two types of efficiency, that is the isentropic efficiency of the compressor and the isothermal efficiency of the compressor. Now we will see this numerical on this efficiency. So we can see here that air is compressed by an adiabatic compressor from 100 kilopascal and 12 degrees centigrade to a pressure of 800 kilopascal at steady rate of 0.2 kg per second. So here, if the isentropic efficiency of the compressor is 80%, determine what we have to determine: the exit temperature of air and the required power input to the compressor. So here if you see, air is compressed by an adiabatic compressor from initially P1 is equal to 100 kilopascal and T1 is equal to 12 degrees centigrade to a pressure of 800. P2 is equal to 800 kilopascal, and the rate of this thing, mass rate, is equal to 0.2 kg per second. Efficiency of this thing is given 80%, that is 0.8. These things are given. Now we have to find out the exit temperature. If it is a isothermal process, so exit temperature is, I think, well known. So we will see here that we know only one property, that is pressure at the exit state, and we need to know one more to fix the state or state postulation and thus determine the exit temperature. The property that can be determined with minimal effort in this case is H2A. Since the isentropic efficiency of the compressor is given at the compressor inlet. So this we can see here that we have to, here P1 is given 100 kilopascal, T1 is given this, P2 is given this, air compressor m dot is given 0.2 kg per second. So we can find out that this is 100 kilopascal and this is the 800 kilopascal. So if we find out from here, 1 to 2s is your isentropic compression and 1 to 2a is actual compression. So we know that H2s minus H1 divided by H2a by minus H1 is equal to efficiency. Efficiency is given, H1 is also given, and so we can find out by this. So T1 is equal to 285 Kelvin. H1 we can find out from the table at this given temperature and the pressure. We will get 285.14 kilojoule per kg. This is from the table. Okay. Now, the enthalpy of the air at the end of the isentropic compression process is determined by using one of the isentropic relations of ideal gases. So if it is the isentropic, we will use the PR2 by PR1 is equal to P2 by P1. It is the isentropic compression process. So here PR1 is 1.1585. The P2 is 800 and P1 is equal to 100. So we can put here, then we will get this value is equal to 9.2672. So we got the pressure at the point 2, we got 9.2672 for the reversible case. And so we got PR2 is equal to 9.2672. So here in this pressure and the temperature, we can get this H2S. Here H2S. This from the table, at this pressure, we will get H2S is equal to 517.05 kilojoule per kg, and this is also from the table. Substituting the known quantities into the isentropic efficiency relation, we will get, this is the relation for isentropic. We know that efficiency eta C is equal to H2S minus H1 divided by H2A minus H1. So here we know this is the 0.8. 0.8 is equal to H2S, we got 517.05 minus H1, we have got 285.14 divided by H2A minus H1, 285.14. So we can get H2A, and by this we will get that 0.80 here is equal to 517.05, this one which we have got, and this is the H1 here, this is H1 divided by H2A minus 284.14. So from here we will get the H2A. So H2A we will get 575.0 kilojoule per kg. So if we got this H2A, we can find out the temperature, and in this case the temperature from this H is equal to MCP delta T. So here we can find out the temperature by this, and T2A we will get 569.5 Kelvin. So we got the first problem, that is the temperature of the exit. Now we have to see the part B. The required power input to the compressor is determined from the energy balance for steady flow devices, and this energy balance is E rate of energy at input is equal to rate of energy at output. So rate of energy is equal to m dot h1 plus w dot a in is equal to m dot h2a. So in energy plus work energy of the total out energy. So here we know that w dot a in is equal to m dot h2a minus h1. So m dot we know 0.2 kg per second, h2a we got 575.03, this one, and h1 we got this one. Putting this value, we will get the WA in is equal to 58.0 kilowatt. Okay, so one thing we got here. Now we have to find out the volumetric efficiency. So in this way, we can get this answer, that how much work is required. So the required power input is 58.0 kilowatt, and that is the answer for this problem. Now we will go for the next topic, which is the volumetric efficiency of the compressor, and that we will see in our next topic. So next topic is volumetric efficiency of reciprocating compression, and in this we will see that the volumetric efficiency of the reciprocating compressor is defined to account for the difference in the displacement volume or the swept volume and the suction volume of the air to be compressed. So it is the volumetric efficiency of a reciprocating compressor is defined to account for the difference in the displacement volume or the swept volume and the suction volume of the air to be compressed. The volumetric efficiency for reciprocating compressors ranges from 65 to 85%. So this volumetric efficiency is depend upon the swept volume or the displacement volume and the suction volume. These two volumes are very important. So the ratio of the fluid delivered by a piston or a ram pump per stroke to the displacement volume of the piston or the ram. So this is the first definition of the volumetric efficiency. The ratio of the fluid delivered by a piston or the ram pump per stroke to the displacement volume of the piston or the ram. So how much amount of you are delivering and how much it is the stroke of your cylinder, that is called the volumetric efficiency. The ratio of the air or gas air mixture drawn into the cylinder of an internal combustion engine to the volumetric displacement of the piston. So it is the how much it is sucking or how much air it is actually going and how much is the real volumetric displacement or the stroke volume of the piston is called the volumetric efficiency. So if you see here, this is the your your VC. It is the clearance volume, and from here to here is a VS or the stroke volume or the swept volume. So ratio of how much air is exiting per stroke divided by VS, that is called the volumetric efficiency of the system. So now we will derive the volumetric efficiency of a reciprocating engine. So it is defined as the ratio of the actual volume of air sucked into the cylinder during the suction stroke to the piston displacement or swept volume of the cylinder. So it is a real case how much it is sucked and how much it is delivered. So it is the ratio of the sucking volume divided by the swept volume or the displacement volume of the cylinder. It is referred to as free air condition, that is the temperature and the pressure of the environment, which may be taken as the 15 degrees centigrade and 101.325 kilopascal if not mentioned. This value you have to remember. If you in your problem these values are not given, you have to put this value as a standard value. Free air delivery is the volume of the air delivered being reduced to free air conditions. In case of air, the free air delivery can be obtained using perfect gas equation. So free air delivery, FAD, is the volume of air delivered being reduced to a free air condition. So how much air you are delivering and it is reaching to the free air condition. So this can be obtained from the perfect gas equation. So what is the perfect gas equation? PAVA by TA. This is the atmospheric condition is equal to P1 V1 minus V4 by T1. We can write it as a P2 V2 minus V3 by T3, T2. So here this you can see in this diagram. Here is the stroke volume, from here to here is a stroke volume, and this is the volume sucked. Actually, this is the sucked. So here if you see, this is the V1, this is the V1 here, this is the V4, this is the V3, and this is the V2. So PAVA by TA at atmospheric condition, this is equal to P1 V1 minus V4. So this is the only from here to here, it is V1 minus V4 divided by T1. That is the state 1. Now for the state 2, P2, V2 minus V3. V2 minus V3 divided by T2 for the state 2 here. This is the state 2 and this is the state 1. So PA VA by TA is equal to P1. V1 minus V4 by T1 is equal to P2. V2 minus V3 by T2. So this is the equation which we have got. Now volumetric efficiency referred to free air condition, and we can see that the eta volumetric efficiency is equal to volume of the air sucked referred to free air condition divided by swept volume. So how much volume is sucked? It is V1 minus V4. Only this much volume is initially it was sucked. And how much is the swept volume? It is from V1 to V3. V1 minus V3. So V1 minus V4 divided by V1 minus V3. So for V1 minus V4, for V1 we can write that Vs plus Vc. Vs stroke volume plus Vc. So Vs plus Vc minus V4 divided by V1 minus V3 is equal to Vs. So Vs plus V1 minus V4 by Vs. So if you divide this thing, Vs, 1 plus Vc by Vs minus V4 by Vs. So we will see in the next that here Vc is the clearance volume and Vc is equal to V3 and the Vs is equal to V1 minus V3. So we will see here that the volumetric efficiency eta volumetric is equal to Vs by Vs is equal to 1 plus Vc by Vs minus V4 by Vs. So now we can see that this V4 by Vs we can make it V4 by Vc into Vc by Vs. Chain rule. So now here we can make V4 by Vc is equal to V3, V4 by V3 into Vc by Vs. So let the ratio of the clearance volume to the swept volume Vc by Vs be given by the clearance C. Let this Vc by Vs number is given as the C. So we will get here that C is equal to Vc, this Vc by Vs is equal to a ratio, it is called the C. So now we will get the volumetric efficiency is equal to 1 plus Vc by Vs is equal to C minus V4 by Vc, V4 by V3 we can write minus C V4 by V3. So the volumetric efficiency of the system is equal to 1 plus C minus C V4 by V3 we can write as P2 by P1 to the power 1 by N by the constant gas equation. So we will get here the efficiency, the volumetric efficiency of the system is, this is the volumetric efficiency of the compressor is a function of the C, where C is the ratio of the clearance volume to the stroke volume. So 1 plus C minus C P2 by P1 to the power 1 by N. So this is the equation for the volumetric efficiency of a reciprocating engine. Now in the next class we will be seeing some numericals on heat conduction, numerical on the heat conduction, and we have some references, P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition. Then second, I have the reference, Yunus Senegal. Most of the problems and these things are taken from this book. Okay. Now we will see that any questions you are welcome to ask. My email ID is ydwedi@gmail.com, and I also request to like and subscribe this channel and give the comment if you want any type of queries. You are welcome. Till then, goodbye, see you, and thank you very much for joining this class.
Like, share and subscribe. Hit the bell icon for more updates.